Everyone, welcome to a series of recordings that I'm doing on datacenteroverlords.com. My name is Tony Burke. You can find me at tburke on Twitter, that's TBOURKE, or on datacenteroverlords.com. And right now I want to do a little quick bit about how routers are sadistic, or basically how Traceroute works. So if you have your client here, so draw a computer, maybe you've got like a really old computer, and you're connected to a router, which is connected to a router somewhere, which is connected to another router somewhere, and connected to another router somewhere, which is connected to your server. In this case, I don't know if you recognize this server here. Just draw these colorful lights on here. So this is basically War Games. So that's the Whopper right there. So there are connections between you and the server that you're trying to reach. Various routing protocols and policies are in place in between you and these other routers, but they are a mystery to you. When you make a TCP connection to a host, SYN-ACK, TCP connection, or UDP, or whatever's going on between you and there, you don't know what's going on in between. You don't know what routers are in between you and the remote host. So that's where Traceroute comes in. Now, Traceroute works because routers are sadistic. I'll show you what I mean in just a second. But first, we have to talk about a characteristic of IP packets. So I've got an IP packet on here. One of the header values is called the TTL. The time to live. Now, this is a loop avoidance mechanism. So when you generate an IP packet, it's set with a TTL, say 64. Every time you hit a router, the router decrements that by 1. 63, hit another router, then it's 62, hit another router, and it's 62, hit another router at 61. By the time you get to your destination, maybe you're like 48, and that's okay. 48 means you get to live. You get to live all the way to your destination. If a routing loop occurs, which they can occur, every time you pass a router, your TTL gets decremented by 1, and then the packet is killed. So that limits the damage caused by routing loops. If you think back to what a bridging loop is, Ethernet frames don't have a TTL. Ethernet frames live forever. But IP packets have a definite lifespan, just like Logan's Run. And when the TTL gets to 0, it's that packet is discarded. The little light on its hand goes off. So we can actually use that in Traceroute. So if I generate a packet with a TTL equals 1, I'll forward it to my destination over here, the Whopper. So let's say my IP address here is 1.1.1.1. This router is 2.2.2.2, or it has an interface on 2.2.2.3, 3.3.3.3, 4.4.4.4, 5.5.5.5, and then the Whopper is 6.6.6.6. If I send a packet with my source IP address of 1.1.1.1, my destination is 2.2.2.2, but I set my TTL to 1, this router is going to get it, and it's going to see the TTL is 1, and it says, I can't do anything with this because I have to decrement it to 0, which means I have to destroy it. So I'm going to kill it. But the routers aren't content to kill anything silently. They have to tell you they did it. So they send you an ICMP message saying, I just killed your friend. I just killed whatever you were trying to send to. I just killed it. And here is my source address. All right, so now we know the first hop. So we send another packet the same way. Now, most of the time these packets are ICMP. So I'll send a ping all the way along. Or I can do UDP. I can send it to an undefined port, or even I can even send it to TCP. I can send an IP packet with a TCP data segment encapsulated in it with a destination address of 6.6.6.port 80, for example. But typically it's I think with Windows it's UDP, and Linux it's ICMP, or vice versa. Either way, we're sending a packet. We're setting the TTL, whether it's ICMP, TCP, or UDP, whatever. The TTL is in the IP header. So it's in the layer 3 header, not the layer 4 header. Send it for 2. This router says, okay, you're good. I'll send it to you. And this router says, now I have to kill you. And then it murders that packet and then sends an ICMP. Say, hey, I just murdered your packet. My IP address is 3.3.3.3. And so on and so forth. And we keep on doing that until we actually get to the destination. So that's why you see that when you do a trace route, you see 1 line, and then 2 lines, and then 3 lines, and then 4 lines, and 5 lines. It's sending these packets, and the routers along the way are murdering those packets and sending it along. Now, sometimes these routers get really busy. Their control planes get really busy, so that hey, I just murdered your friend packet, that one can get put away, or just, I'm too busy to tell you that I just murdered your packet. So that's why sometimes you see timeouts. Other reasons why you see timeouts is if, like, for example, I have an ICMP filter. A lot of security a lot of routers will sometimes turn off all ICMP, which is not really a good idea, because you block useful messages like this. Like another useful message is your MSS clamp, your maximum segment size clamp, saying, hey, path MTU discovery. The MTU on this particular link is a little bit lower than what you're used to, so you need to clamp down your maximum TCP segment size so that you don't get fragmented or discarded. So it's not a good idea to block all ICMP. But yeah, so that's how Traceroute works. Traceroute works because routers are sadistic. They will kill packets with a TTL when there's no life left in their TTL. And not only do they do that, they will tell you about it. They're not content to just kill it. They're going to tell you about it. So that's how Traceroute works. Hope that helps clears things up. And my name is Tony Burke. Again, you can find me on Twitter at tburke, at TBOURKE, and datacenteroverlords.com. Thank you.